Here, we're going to find a linear function that models this numerical data. So we're given a collection of ordered pairs. And since we're looking for the linear function that models this data, this is just a subset of all the ordered pairs. And you can see that we have -3 going to 0, 0 to 3, and 3 to 6. And then we have, as you go from the X values from 1 to the next, you can see it increases by 3 every time. And here it increases by 4 every time. So the X values represent the run. When you go from -3 to 0, the run is 3 because you're adding 3 to -3 to get to 0. Similarly, when you go from 0 to 3, you're adding 3. And when you go from 3 to 6, you're adding 3 to get to from 3 to 6. So each time you're adding 3. So the run is +3. This shows that the run is +3. Then if you look at the Y values, you're running from 5 to 9, you're adding 4. And here from 9 to 13, you're adding 4. And then from 13 to 17, you're adding 4. So the rise is +4. And to find the slope, you take the rise over the run, which is going to be 4 divided by 3. Okay, now we need the intercept to find a linear equation for this data set. And the y-intercept is when x equals 0. So if you look at your data here, you can see x equals 0 right here. And the corresponding function value or the corresponding y value is 9. So the y-intercept value now your book would say y-intercept is 9. Technically, that's not accurate because the y-intercept is a point, but the y value of that point is 9. So we say the y-intercept value is 9. At least this is how I say it. Okay, so now we have enough information and we just have y equals 4/3 x, that's the slope, plus the intercept value, which is 9. And so this is the linear function that models our data. And of course, you could write it as f of x equals 4/3 x plus 9. Both work since y equals f of x.